All right, so we started to do the linear chain problem. We started to do the linear chain and writing out what this looked like in, I guess I'd call it real space, your infinite tridiagonal matrix where every row is the same, shifted over by one. We actually calculated it and went through the finite, showed the finite difference gives you the same thing. Mentioned Bloch's theorem and then for the first time introduced this basis transformation into this Bloch sum basis, which is what we're going to be using over and over again. So we start with our localized orbital basis, and in general this will be more than just s orbitals and p orbitals. And we do this unitary transformation. And so for each n there's going to be a k. So before our index is this like n for each atom, and really it's going to stand for each unit cell, the repeat index of the crystal, so there could be 2 atoms per unit cell, for example. And then, so this index then becomes this index over here, which labels in our new basis in k space. And so that for each n, there's going to be a k, a one-to-one mapping from your localized orbital basis to this Bloch sum basis. I showed they're orthonormal, sort of. Have to take my word for it that you only get matrix elements between the same k, and once you set k equal to k prime, it's trivial to show that they are normalized, properly normalized. And then I went ahead and took the matrix element of the Hamiltonian between 2 of these, and for this simple 1D chain, I mean this is the eigenstate, so I immediately get that this one matrix element is in fact this that we've calculated before, which is our relationship between E and K. Okay, so we said when we go to this Bloch sum basis, it's a one-to-one mapping between our index n, which is your periodic, it's the index for the repeat unit in your crystal, the unit cell. N is the index for the unit cell, and K, and there's a one-to-one mapping, so for each n you have a K. And let's just look at one dimension where we have our linear chain, and formally this comes about via periodic boundary conditions, which you've probably run into before. So if I have a linear chain of atoms, dot, 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 boom, you label them from 0 to n, dot, dot, dot to n. So there's my linear chain of atoms going from 0 to n, my indices. And the phase factors, the phase factor is e to the I, k, n, a, where that little n is the index from 1 to n, or 0 to n. Right? That's your phase factor. And so for periodic boundary conditions, I need the phase of the first atom to be the same as the phase of the last atom. That's what we mean by periodic boundary conditions. So, for n equals 0, the phase is, e to the I, k times 0 is 1, right? So the phase of the n equals 0 atom is 1. Right? And so and that also for our periodic boundary conditions has to be the phase of the last atom, which is e to the I, k, n times a. And note that NA is equal to the length of your chain. Right? NA is the length of your chain. Or A is the spacing. Right? NA would be the length of your chain. And so that means, for that to be true, that K has to equal any integer n times 2 pi over NA, which is n times 2 pi over L So that is your how n and k map onto each other. All right, so for every n you get a k, vice versa, a one-to-one mapping. And what they call the thermodynamic limit, which is what we always do, we let L go to infinity, so k becomes a continuous variable. Right? As L goes to infinity, k becomes a continuous variable. And we can turn sums into integrals. And so we're going to be doing this a lot, so let me just, so this is sort of an accounting trick to keep, because in the end we let, L go to infinity, and so it's like, well, why bother to go through all these hoops since it becomes a continuous variable? But it allows us to turn sums into integrals. So often you'll see in solid state textbooks and in this course, we'll be writing down things like a sum over k, and to actually evaluate that, you have to turn it into an integral. So in 1D, the way you would do that is you multiply by 1 over delta k. You have your sum k. You put your another delta k in there, right? This is, I haven't changed anything. And then as you let L go to infinity, that delta k becomes a true infinitesimal, right? And delta k becomes a true infinitesimal, and so you get L over 2 pi integral dk, right? And the limit is we let L go to infinity. Okay, it may bother you, we have an L out front, which we're letting go to infinity. But in reality, what you're going to see, we always are going to have something in front of our sum. We'll have something like a 1 over L in front of our sum. And so that becomes integral dk over 2 pi of whatever you're integrating or summing. And that very suspiciously looks like the integral you do for a Fourier transform, going back and forth from real space to k space. Right? In real space, you just do like dx, and going inverse Fourier transform, you'd have dk over 2 pi. Or for you EEs, you'd have dt for going one way and d omega over 2 pi going back the other. And so that's 1D. In 3D, multiple, or 2D or 3D, we're going to be doing all of these. So in 2D, like for graphene, in 2D, you just let, you have like an Lx in the x direction and an Ly, and you go through the same, and in your area, the area is just Lx times Ly, right? L squared. We're going to let the L's be the same, which is just L squared. And so in 2D, you're going to run into a sum like 1 over the area, sum k, which is going to become integral d squared k over 2 pi quantity squared. And in 3D, and the same, going through the same steps, you'd have 1 over volume sum. Now you'd have a 3-dimensional k. Will be your integral d cubed k over 2 pi quantity cubed. So it's just sort of, periodic boundary conditions defining what we mean by delta k, relationship to L. Sort of an accounting trick to keep track of all this appropriately. Okay, so that's this mapping between n, the index that is for the unit cells, and k, the index for k. Okay, now let's move on to something a little more complex. So now we're going to go to we're going to stay in 1D. We're going to stay in 1D for a while. It's easy. But now we're going to have two atoms in a unit cell. And we're going to have two different kinds of orbitals. And these are going to be an s orbital and a pz orbital. And they're going to alternate depending on which atom you're on. So this is going to give us a two band, so it's called a two-band model. You're going to have one conduction band and one valence band. So up to now we've just had a conduction band, single band. And it actually suffices in many instances to model the direct gap 3,5s like gallium arsenide, indium arsenide, etc. So it is, in many instances, a reasonable model for the conduction and light hole band. Conduction of your direct gap 3,5 semiconductors. And it's sort of like a cartoon model. It captures, just like our little two atom thing you did for your homework, it captures the fundamental physics of the light hole band and the conduction band. It's a caricature. A caricature is a good description of it. So I don't know if you know what defines a caricature, but it's you take, say, you're going to caricature someone. You take that someone and you sort of emphasize their defining characteristics. So you're all way too young. You know, back in the day, there were all these caricatures of President Nixon, you know, and he'd have a very long nose and big ears and shaggy cheeks, you know, and this is a caricature. So you take the defining characteristics and you exaggerate them, and this is sort of what this model is. We're going to see that when we do this, we're going to get our two bands, our conduction band and valence band, and we're going to find that right at k = 0, at the gamma point, the conduction band wave function sits entirely on the cation, and the valence band wave function sits entirely on the anion. So now we're going to have two atoms in our unit cell will represent, say, the gallium and the arsenic atom. And if you think we're in the periodic table, you've got your gallium and your arsenic. So as you move this way, it's more electronegative. You're going to have a larger ionization potential. And so, you know, the site energy of the arsenic will be below the site energy of the gallium. And so you would think that in the bonding state, you know, the wave function wants to sit more in the lower orbital. That's what you saw in your homework, and that's what we're going to see, except in this model in your valence band, which is your bonding, your lower energy, your bonding band. The wave function at k = 0 sits entirely on the anion. So we see, you know, when we do the model more accurately, the wave function is heavily shifted towards the anion. Here it sits entirely on the anion, and in the conduction band entirely on the cation. Okay, so let's start drawing some pictures of what we're talking about. So in each unit cell, I'm going to have two atoms, and they're different now. I'm going to have, say, an arsenic and an indium. Two atoms in my unit cell. I don't know if I can do this. Okay, and so my repeat unit is now this. So that index n stands for each one of these things. It does no longer correspond to the atom. It is the index of the unit cell. This is my lattice constant. Right? The lattice constant is always the length of that repeat unit of your crystal. And so this will be my arsenic So it'd be indium. And the basis I'm going to choose, I'm going to put a p orbital, pz, so this would be my z direction. I'm going to put a pz orbital on my arsenic atoms and an s orbital on the indium atoms. Okay, that's my basis that I'm choosing. And p orbitals, unlike s orbitals, have a sign. So this side of the orbital is positive, this side is negative. Positive, negative, positive, negative. So your wave function is positive on one side, negative on the other.
Why is that?
It's the p orbital.
Is positive meaning spin up, or positive meaning?
No, just like the sign of your function. The sign, it's just a function in three-dimensional space.
The p orbital has three different.
There are three different p orbitals. We're just using one.
Okay.
There's a px and a py, which we're ignoring.
So those, okay.
And if you think of px and py, they're going to have much. Well, we'll get into that. For now, since I'm. Oh yeah. Okay. Let's just not even go there at the moment. Yeah.
Some people I've seen they use the P1 or P2 orbital. What's the difference?
Between what's
for example, they say P1 plus or P2 minus.
So that's probably referring to the sphere labeling in terms of the spherical harmonics, right? Like y11, y10, and y1 -1. I'll get to that later. Right? A PZ is a linear combination. Well, actually, PZ is just y10 in terms of the spherical harmonics. Right? I mean, I don't know. You've probably all seen, vaguely the solution of the hydrogen atom, right? And the solution of these spherical harmonics, right? The YLM functions. Doesn't ring a bell. So, I mean, the ground state of the atom is the s orbital, right? The next excited state are the p orbitals. And you know that the ground state is always symmetric. And look at this thing. The next excited state is antisymmetric. Just like what we've already learned from our little two atom problem.
And it's always positive on that right side towards the other atom, correct?
That's a convention. But once you choose your convention,
okay.
You got to stick with it for all the p orbitals.
Okay.
You can't just be arbitrary. So once you choose the direction of z, that chooses your sign convention.
Oh, the z determines it. Okay.
I chose my z-axis pointing in that direction. All right.
In this figure, that is what we call belong to the conduction band. Yes.
What's that?
In this figure, s orbitals belong to the conduction band. Yes.
We will see that is true. But right now, there's no, we have to calculate that. We will see that the conduction band at gamma is entirely s orbital. Yeah. And the valence band at gamma is entirely p orbital.
Is it always true? Or?
Well, as you move away from gamma, it becomes mixed. Only right at k = 0. Okay. I mean, if it were always true, the atoms wouldn't be talking to each other. Right? I mean, because I only have s orbitals on the indium atoms. It'd be like they don't know anything about it. You got to mix up the orbitals to create them. Anyway, okay, so this is our basis in our localized orbital representation. And as usual, each atom is going to have the potential. I'll just draw this little Coulomb potential for each atom, just like we drew before, et cetera, et cetera. So this part of it is the same. We've got our little Coulomb potential. For each atom, we're going to again consider our two center integrals, just like we did before, where you only consider nearest neighbors when you calculate the matrix element. So it's our nearest neighbor tight binding model. Okay, nearest neighbor tight binding model. And so just like for our 1D chain, let's see, what do we want to do? Let's look at the matrix elements. So let's start with the easiest one. So I have a diagonal element. Remember the label is n. So I'm labeling, so this is, we call this like n minus 1, n, and n plus 1. So we're labeling each unit cell by some index. And so Sn H Sn, going through the same things that we did before. This is just going to give me, an EC tilde, and at this point I'm not even going to worry about the tilde, right? You're just going to get some little shift because there's some potential nearby, and I'm not worried about the shift. It's small compared to and it sort of doesn't qualitatively change anything. What we're really interested in is the off diagonal elements. So this is EC, where C stands for our cation, and similarly I'm going to have a PZNH, PZN equal. This is going to be a different energy because it's a different type of atom, just like what you did in the homework, the energy for your anion. And of course, what's interesting now is the off-diagonal elements. Those are the diagonal elements. Now let's look at like matrix elements between, I think just to keep my sanity, I've got to give my atoms their own numbers, sort of beyond what I've labeled for the unit cells, so we know exactly what I'm talking about here. 1, 2, 3, 0. Just giving some numbers to my atoms. Since there's 2 atoms in a unit cell, and it kind of gets confusing. And so, let me look at the matrix element between atom 0 and atom 1. Or, yeah, okay, and let's just do atom 0 and atom 1. And I need to keep my picture here so I won't get confused. So I'm looking at S0 and our usual p squared over 2m plus v0 plus, or u0 plus u1, plus the potential due to atom 0 plus the potential due to atom 1. This is our usual nearest neighbor type binding model, or in our two-center integral p z1. So that's what I'm looking at, the matrix element between atom 0 and atom 1. We go through the usual steps that we went through when we just had all s orbitals, and this is equal to S0 times this average of the two potentials, PZ1. Just going through the exact same steps we went through in our linear chain model with all s orbitals, or the one you just went through with your homework. All right?
Are those potentials all going to be the same?
Yep. Well, for a given type of atom, they're all the same, but they're different for atom. They're different for arsenic than indium.
So, okay, I'm just trying to understand the reason why you're taking this average. Is it just to make it look nicer, or is it?
Yeah, physicists like to make everything look symmetric.
I mean, could you just substitute it as just saying, instead of potential 0 plus potential 1, could you just say potential 0? Would that be the same thing? If they're the same.
Let me see. Yeah, I mean, it could either be V0 or V1.
So
Could
You can
either
do-
be
you can do-
V0 or V1.
Because they're the same thing, right? So it doesn't matter.
But the potentials are different. It's just that, I mean, you know, so the potential of V0 is sitting over here, right? Here's my V0, here's my V1. And so they're in different locations. One is going to be more predominantly acting on the PZ orbital. One will be more predominantly felt by the S orbital.
Okay.
But the matrix element is going to be the same.
Okay.
But the important point here is actually not that. It's for the first time, we really need to stop and think about the sign of this matrix element. So if we look at the 0 atom and the 1 atom, and we know that both of the potentials are negative, for the sign of this integral is going to be what? I mean, when we were doing just s orbitals, what was the sign of that off-diagonal matrix element?
Negative?
Yeah, it was negative, because the s orbitals were positive, the potentials were negative. But now look at the sign of that p orbital that's going to contribute mostly to that integral. Right, the p orbital in atom 1. The lobe of that p orbital that's really contributing to that integral, that's overlapping with the s orbital in atom 0, is negative.
Sorry to please repeat one more time. The sign, actually, the sign of the, why you said that it is negative.
Of this p orbital?
Yes.
Because I drew a negative sign on it.
No, I mean, the potential. I mean.
Oh, the potential?
Yes.
Oh, that's that's the Coulomb potential between a positive ion and a negative electron.
Yeah, okay.
So the sign is negative e squared.
Okay, so the integral.
So I have the total potential is negative. The s orbital is positive definite. And the sign of that p orbital that's contributing predominantly to the integral is negative. So I got two negatives and a positive, right? Negative potential, negative orbital, and a positive orbital. So that's going to give me a positive integral. Right? Two negatives and a positive. That's positive. Right? Two negatives and a positive. Negative 1 times negative 1 times 1.
So the negative side of the arsenic atom, so
Yeah.
and then the positive side, and then the negative of the indium, whatever the atom is.
Indium.
Indium.
Atom 0. We're looking at atom 0 and atom 1.
Okay.
Got it?
Yeah.
Atom 0 and atom 1. Okay. And now if we look at, without further ado, if we look at, so this is going to equal, what's going to be my notation? That's going to equal T, which is greater than 0. So now we're getting an off-diagonal element which is greater than 0.
Can you remove the kinetic energy here?
Okay, I'll go through it. I mean, in the same way we've done before, in your homework too, right? That kind of drops out because it's the kinetic energy, you get the on-site energy times the overlap integral, which, since we've assumed an orthonormal basis, is 0. So let me just write it out. So that integral, well, first let me paste this so I don't lose my picture. Okay, so what we were looking at S0 p squared over 2m plus u1 plus u2 times what, pz1. And that's equal to S0 pz1 EA plus S0 V0 PZ1, and it's also equal to S0 PZ1 E epsilon C plus S0. I'm mixing up V's and U's, sorry. My V and U is the same thing. V1, PZ1. And so these first terms are coming out of that the kinetic energy, like this is coming out of these two terms, with this thing left over, U2 left over, right? And when I do it the other way, you know, this is coming out of the p squared over 2m plus the U2 term, with the U1 left over. And these disappear because we've assumed these orbitals are orthonormal. Okay, it's just like what you did in your homework, what we did with the little 2-atom problem. Okay, now we need to look at the matrix element between, so we did 0 and 1. Now let's look at the matrix element between atom 1 and atom 2. So atom 1 and atom 2, we're going to have PZ1 H S2, and all we have to do is look at this. We go through the same steps as what we did, but now I've got the positive sign of the p orbital facing my s orbital, which is always positive. And so now and my potentials are always negative. They never change. And so now I got two positives and a negative in that integral. So this is going to be negative t. So now when I construct my Hamiltonian, the off-diagonal elements are changing sign as I go down that chain of atoms. Okay? These matrix elements are flipping signs as I go down that chain of atoms. Okay, so this is always the first step. Just figure out what the matrix elements are, their signs in your localized orbital basis. The next step is to form your Bloch sum basis. So for each type of orbital, you form a Bloch sum. For each type of orbital on each type of atom, you form a Bloch sum. In this case, we have, you know, each atom has its own type of orbital. Later, we'll have each atom with multiple types of orbitals, but in this case, there's only one. So I've got my s orbital on the cation becomes this Bloch sum of s orbitals. So this is just for normalization. So this thing is normalized. This sum over n is over the unit cells, the repeat units. And we're going to do this since our anion is over here. Here's our anion, this orange-red guy over here. We're going to, in terms of position, we're going to call the position of the anion to be Na. In other words, we're like the beginning of each unit cell we're going to put right on the anion. And so this guy, we're going to assume they're equally spaced. This guy is in the position of this guy, the cation is going to be Na plus A over 2. So this is Na plus A over 2. That would be the position of the cation, right, shifted by half a lattice constant. And just assume they're all equally spaced. So I'm going to add that phase into my Bloch sum. So I have e to the I kaan times e. I don't have to do this, but for a lot of things it makes keeping track of everything easier. E to the I k a over 2. So this is for the cations. So that's just the my periodic part and my phase factor. And so for the p orbitals, I have pz, same deal, 1 over root n, sum over the unit cells, pz orbital in each unit cell times its phase factor. This is for the anions. Okay, so the only difference is I've added this extra phase factor to the cations, which are shifted by A/2, putting the origin of each unit cell on the anion. And now in this basis, I need to calculate the matrix elements of the Hamiltonian. So let me go ahead and do that. So we need to, well, we start off with a simple one, SK. Okay, so, and this is why you first have to figure out what the matrix elements are in your original basis, because the only way to evaluate this is to sort of substitute back in your original basis. So this is equal to 1 over n, right? I get a 1 over root n from each one of these guys, so 1 over n, sum over n comma m, Sn h Sm e to the I Ka m minus n. And then you have to remember that in this picture, in this crystal, and in these crystals, real crystals in general, then all of the nearest neighbors of an cation are anions. So all of the nearest neighbors of the cations are going to be anions. And this is true in general, even when we go to 3D and gallium arsenide, right? Each cation is surrounded by its, for gallium arsenide, 4 nearest neighbor anions and vice versa. In our 1D picture, each cation has 2 nearest neighbor anions. And so there are no nearest neighbor cation matrix elements. So when we look at this Hamiltonian matrix element, the only ones that contribute here in the sum are when n equals m. In other words, when it's the same atom. So the only time this contributes is when n equals m. So this just gives me, this is why we had to do this first. This just gives me EC delta n comma m, that matrix element in there. And when m equals m, that just kills off my phase factor. This is sorry, 1. I get a phase factor of just 1. When m equals n, that just becomes 1. And so every term I've killed off the sum over, say, choose one, m, and so I just get that's equal to EC, which is the same, independent of the index, 1 over n, sum n, and then the sum over n just kills this, and that just gives me 1. That's why we have that normalization factor. So it's just equal to EC. So in either basis, our Bloch sum basis or our localized orbital basis, in a nearest neighbor model, you're always going to find this true, that the diagonal element is just what it was before in our localized orbital basis. And of course, the same thing's going to hold true for the p orbitals. So without further ado, we'll just write that down. PZK H for the anion A. And just going through the same procedure. And now the interesting, of course, all the physics is in the off-diagonal matrix elements. So let's look at SK H PZK. All right, so that's going to equal 1 over n sum n comma m Sn h PZM and our phase factor e to the I Ka m minus n minus a half, because that we had that extra factor of a half a for our cation. So the cation was sitting at like n plus a half a, right? And the anion is at ma. And since the cation has sort of been flipped around as a bra instead of a ket, its phase is negative. So that's why it's negative n minus a half a, corresponding to the cation. Okay, so again, we look at this matrix element that we have just calculated in the localized orbital basis, this guy. And if you think of what our crystal looked like, say we have, we've got a cation and anion and anion. And so I can get, a matrix element, and our unit cell is, oh shoot, that's not our unit cell. Our unit cell is defined like this, right? We have anion, cation, anion, cation. So I get these two possible matrix elements here. One within the same unit cell and one going from one unit cell to the next. And so that's equal to, and I guess we better put our orbitals back on here, so keep track of our sign convention. Positive, negative, positive, negative. So if we're in the same unit cell, that must mean n equals to m, right? Because these are the indices now of the unit cells. So I'm going to have, if I'm in the same unit cell, I've got a positive orbital here, and this is always positive. The potential is negative, so I get, the integral is negative. I get a negative t times delta n comma m. Right, so if I'm in the same unit cell, I get a negative t. And if I'm going from one unit cell to the next, now I have this negative lobe and a positive. So, and the potential is always negative. So this is when I get my two negatives and a positive, giving me a positive t plus t delta, which is my index, n comma m minus 1. So the index of n is 1 less than m. This is going from one unit cell to the next. And so now, again, this collapse, these Kronecker delta functions collapse one of the sums. So this is equal to 1 over n sum m minus t. And so for minus t, I have n equal to m, so I just get this leftover part from the 1/2 there. So I have e to the minus I Ka over 2. And for this other case, n equals m minus 1, I'm going to get plus t times e to the plus I Ka over 2. Right, so when, so I just put in for n, I'll put in m minus 1, and I'm subtracting it off, so the m's disappear, and I have a plus 1, a minus a half, so that becomes a plus 1/2, and that's why I have a plus I Ka over 2 for the phase factor. And you know, that the argument of the sum is independent of m, so again, the sum over m just cancels the 1 over n, and that's what I'm left with. That's the off-diagonal element in this Bloch sum basis. And assuming I did my math right, I don't have to calculate, you know, the other off-diagonal element, because I know it's got to be the complex conjugate of this one, right? If you're lazy, like me, and you trust what you've done, you only need to calculate one of them and take the complex conjugate, and you've got the other one. Because you know the matrix elements have got to be Hermitian. If your matrix is not Hermitian, you made a mistake. So it's a good sanity check if you don't trust exactly what you've done to actually calculate both and see that one is a complex conjugate of the other. Okay, so now let's see. So we've got this. What do I do with this? This, well, this is equal to, what is that equal to? That looks to me like I've got a t, from factor out of t, times 2I sine Ka over 2. Looks like that is what that is to me. Everyone see that? Because, like, you know, sine of theta is e to the I theta minus e to the minus I theta all over 2I. I know some of you haven't thought. So sine, I'm just using the fact that sine theta is equal to e to the I theta minus e to the minus I theta all over 2I. So down here I have the e to the I theta, e to the minus I theta with the appropriate minus sign out front. And so I just multiply through by 2I, that's 2I sine theta. Right? All good?
What's the meaning of that? The imaginary term? The decay of energy?
The meaning of the fact that it's imaginary?
I think D is also conjugate.
What? T is real.
T is
T is real. This phase is coming purely from, you know, that these phase factors. It's purely a product. I mean, this is where it's coming out of. Right? These phase factors, you know, our basis is no longer real, right? In the Bloch sum basis is not a real basis. It's a complex basis, right? Because I got these phase factors.
So are you saying to ignore the imaginary component of it, or is it? I don't understand.
No, I'm just saying where it comes from. That's all.
Oh, okay.
Its origin. It's a fact. I mean, its origin comes about from the fact that our basis is no longer real in this Bloch sum basis.
Because sometimes they use the e to the I theta to represent sine and cosine more easily, and then they just kind of ignore, when they get to their final product, they'll ignore, unless I'm totally
Like in
mistaken.
phaser stuff. Yeah, that's not what we're doing.
Okay.
But, you know, I mean, since your Hamiltonian is Hermitian, your energies, all observables are going to be real quantities, right? All your energies are real. All your wave function, the observables are the magnitude squared of the wave functions. That's real.
On many problems, the imaginary energy means that.
No, this is not. Okay, this is All right, the units are energy because T has units of energy. But it become, let's see, where does this fact that the matrix elements are not real really? I think we're going to see this when we really start doing like silicon. And since these these matrix elements will have different signs and different either real or not, you're going to find that it gives rise to cancellation and simplification of the Hamiltonian. We're going to be adding a lot of these together when we have like 4 orbitals on an atom. Right now, I don't know. I don't know if the I really does anything at all. I mean, the next thing we're going to do is calculate the energies, and immediately disappears when we take the determinant. So let me write down the matrix, and you'll see that it doesn't seem to matter too much. I can see right offhand. So let me write out our 2 by 2. Whoops, what did I just do? Come back here. Okay, write out our 2 by 2 Hamiltonian. Right, so in this Bloch sum basis, for a given k, I mean, this is the beauty of it in these periodic things, all the k's decouple, so you just do one k at a time. And for a given k, what was this infinite tridiagonal Hamiltonian is now a 2 by 2 Hamiltonian. Of course, you got to solve it for every k. And so our Hamiltonian is now this. For a given k, it's just EC. Well, maybe I should have done the other one. Oh, this is right. Yeah, this is our mission. So minus T 2I sine Ka over 2 T. So this is our H of K. And so the way this is ordered in terms of this basis is it's SK, PZK, SK, P sine PZK. So I go across row column. So this is, this is the matrix element between SK, SK, and SK, PZK, PZK, SK, and PZK, PZK. You choose an ordering to your basis, and you write out your Hamiltonian. Yeah.
Maybe it's not real because the order basis is the eigenket, the eigenstate of the Hamiltonian, but the Bloch the Bloch sum basis is not the eigenbasis.
No, it's not an eigenbasis
So
anymore. No.
So it should be unreal.
Well, it doesn't. It could be real. It doesn't have to be complex.
It doesn't have to be real.
But yeah, it
because
doesn't.
it's not the eigenstate.
It's not an eigenstate, and the basis is no longer real itself. So
Yeah. So I
Also
think
the
that's
same related to the octagon of them.
what's that?
Not,
Yeah.
indicate that it should be real.
I don't think so. Let's just go ahead and calculate. So to calculate the eigenenergies, we do what we always do, and we have to set the determinant of H minus E equal to 0. So to calculate the eigenenergies, we solve H minus E times, formally I'll put the identity matrix there, because E is just a number. So we set the determinant equal to 0 and solve for the E's that make that, the energies that make that true, right? That's how we calculate the eigenenergies. And so that H minus E, I just put a minus E here on the diagonal, right? That's my H minus E. Right, so now that's H minus E. So H minus E. And I take the determinant. The determinant is just looks very much like what you just did in your homework. EC minus E, EA minus E, and then minus the product of the off-diagonal terms, which is 4 t squared sine squared Ka over 2. And you set that equal to 0 and solve for E. And so the only difference in what you did in the homework and what you're doing now, before you just had for the off diagonal, what, t squared, I guess, for your homework. I mean, look at this. You just had t squared for the off diagonal. Right? That's the only difference between this and what you just did for the homework. So if in your homework, everywhere you saw a t squared, you replace it with this thing, you're done, right? Take your homework, everywhere you saw a t squared, replace it with that. 4t squared sine squared Ka over 2, and that's the answer. So let me just go ahead and write it down. So E is equal to EA plus EC over 2. This was your E bar, plus or minus square root, and the next term is your delta squared. I guess the order doesn't matter since these are squared. EA minus EC over 2 quantity squared plus, and this was just, I guess, your 4AC all over. Plus, okay, I'll just write down what's in my notes. 4t squared. I don't think that 4 should be there in the last term. Oh yeah, no, that's correct, because it's minus 4ac, or yeah, all over 2a. All right, so before you just had a t squared, and as I said, wherever you saw had a t squared in your homework, you just replace it by this 4t squared sine squared Ka over 2, right? That's exactly what you had in your homework. So this was our E bar. If we want to write it in that form, E is equal to E bar plus or minus square root of delta squared. Is this how we define delta, this EA plus EC over 2? I can't remember.
It was minus something. I think it was probably epsilon C minus epsilon A.
Over, yeah, it doesn't matter since it's squared.
Yeah.
Well, but I'm worried about the 1/2. Did we include that in the definition?
Yeah, it was
Okay, so this is delta squared plus 4t squared sine squared Ka over 2. Right, just like in your homework. And more generally, I just like, you're going to see 2x2 Hamiltonians a lot. So in general, if you have a Hamiltonian that looks like, what did we just have? It was EC. I'm going to make this general. This is going to be V. Yeah, I'll just call it V of K. V star of K. E. A. Or maybe to use notation more close to what we've got, EC, I'll call it T of K. T is a function of K, where T is, this is just our generic notation for the off-diagonal coupling, but now it's some function of K. This will be the general form for your 2x2 Hamiltonian. This will be the form for graphene in 2D, where K will be a two-dimensional wave vector. Because there's two atoms per unit cell, we're going to put one orbital on each atom. This is a very generic Hamiltonian. And so you look at this and you immediately write down E is equal to E bar plus or minus square root delta squared, I guess delta squared, yeah, delta squared plus the magnitude of this off-diagonal coupling term squared. That's your generic answer for any 2x2 Hamiltonian like this. Okay, you never need to do another 2x2 Hamiltonian. Once you figure out what the off-diagonal coupling term is for graphene, you immediately have the dispersion for graphene, you will see. Okay. We'll leave it at that for the moment. So this is our dispersion. What do we want to do with that? I guess, so we know the energies. I guess we want to look at the form of the wave function. So the wave functions are, well, how are we doing on time? So at K equal to 0, which is called the gamma point in your Brillouin zone, if we look at our expression for the dispersion, so this thing, our T of K squared was our 4 T squared sine squared Ka over 2. So K equals 0, that's 0, right? And K equals 0, that's 0. And so at K equals 0, your Hamiltonian is just EC 0, 0, EA. Right? That's your Hamiltonian at K equals 0, right? And so, I don't need to do anything fancy. If that's my matrix, I immediately know what the eigenstates and eigenenergies are. My conduction band edge, the higher energy, is just epsilon C, because I know that the energy of the cation is a higher energy. Right? The two eigenenergies are just, for a diagonal matrix, are going to be the two diagonal elements, right? Diagonal matrix, the eigenenergies are the diagonal elements. And the eigenstate corresponding to this, so psi gives me a wave function that's just equal to S at K equal to 0. So in terms of my matrix, the wave function psi is just equal to, in terms of the column vector, be 1, 0. So if you want to go through the math, I mean, at this energy, to do my eigen function problem, I do EC minus E 0, 0, EA minus E times, C1, C2, equals 0, and I'm setting E equal to EC. So that means this term is also 0. So, a column vector that gives me 0 is 1, 0, because I'm just multiplying that by a 0 row. So the diagonal is trivial. You don't need to do anything fancy here. And the 1, 0 corresponds to, right, these are the C's that weight my, so in my general psi is, C1 SK plus C2 PZK, right? That's the way I ordered my basis. That's what these column vectors mean. And so in this one, C1 is 1, C2 is 0, so my eigenstate is just this. And so we have to think about what that means. That just means, I can go back and write that out. That's 1 over root n, sum n, s, n. That's what that state is, because k equals 0, right? There's no phase factor. My e to the I k a term disappears, because k is 0. So it just means that you've got your wave function, as I said at the beginning, is entirely sitting on the cation, and it has 0 weight on the anion in this simple model. Right? The wave function is entirely sitting on the s orbital of the cation at the conduction band edge at k equals 0. And you can immediately see, looking at the Hamiltonian down in the lower left, is, if the t, as soon as k is non-zero, my t's show up again, those off-diagonal terms show up, and I'm going to mix, the eigenstates will now become a mix of both the s and p orbitals as soon as k moves away from 0. Right? 1, 0 and 0, 1 will no longer be eigenstates as soon as I have off-diagonal terms. And I pick up off-diagonal terms as soon as k becomes non-zero. But right at k equals 0, the wave function is, the conduction band, this antibonding orbital, what we called antibonding before, is sitting entirely on the s orbital. And if the valence band edge corresponding to my valence band edge is just EA, E, and psi for that eigenenergy is just my P, Z, K equal to 0. Which is my, 1 over root n. I guess if I wanted to be exact, this guy has this phase factor which is independent of n. I could actually pull it out front. This is like my e to the I. There's no, when k is 0, that disappears too. That extra phase factor is gone. No phase factor at all at k equals 0. And I had that extra phase factor of 1/2, but that disappears too. Okay, so the the valence band edge is sitting entirely on the p orbital of the anion. And to go back to our Hamiltonian, just, again, I have this EC, and I put in this value for E, so EC minus EA, 0, 0, EA minus EA, which just gives me another 0, times the eigenstate is now 0, 1, which equals 0. And so this is my C2 equals 1 and C1 equals 0. Going back and forth between looking at the column vector and and the actual state, which is the sum of localized orbitals. Okay, so as I said, this is sort of a caricature. If you think about, the energies of the atoms, I've got my, anion, EA, my cation, EC, and in the valence band, the lowest state, I'm sitting entirely in the PZ orbitals in the valence band, and in the conduction band, I'm sitting entirely on the cation in the s orbital. So the valence band is entirely p-type at k equals 0, and the conduction band is s-type. And this is actually true for the real material, the 3 5s, right? At k equals 0, the valence band is entirely made up of p orbitals, and the conduction band is entirely made up of s orbitals, right at k equals 0 for the 3 direct gap materials, gallium arsenide. So I guess one important thing that comes out of this is that at k equals 0, your wave function has no phase. It's just the only thing that exists is this repeating unit, right? Which is the same in every unit cell. It's just the same, identical. It has no phase since the e to the ka term is 0, and it's just the wave function itself repeats every unit cell at k equals 0. So that's what a gamma function looks like. It has no phase. And the other thing we can look at and understand is the nature of an x wave function. So we've looked at gamma, and now we can look at the edge of the Brillouin zone. And in crystallographic notation, that's called the X point in your Brillouin zone. It's the edge of your Brillouin zone. So in 1D, which is all we're thinking about, we have our gamma point at k equals 0, and we go from 0 to pi over a and negative pi over a, and these are equivalent points, and they're just all labeled as X points. So we just looked at the gamma point. Now we're going to look at the nature of the wave function at the X point. And so at X, if we look at the conduction band edge, the energy, EC, is equal to our E bar plus square root. And if we think of physically what that delta is now, delta was our EC minus EA. But from this, I guess this is the other thing. From this, we know that delta, okay, if we look at k equals 0, E bar, E equals E bar plus or minus delta, right? At k equals 0. And that means that, what's that mean? Delta is just your band gap divided by 2. Delta is your band gap divided by 2. Because if you go back and look at this dispersion relationship, the minimum energy of the conduction band and the maximum energy of the valence band occur at k equals 0. Right? They're only going to get larger as k becomes greater than 0, because this sign term is squared. Right? So as k becomes greater than 0, this is positive definite. It only gets bigger. And so your minimum gap occurs at k equals 0. Right? Your minimum gap occurs at k equals 0. That's why it's a direct gap model. Right. And so this delta is my band gap divided by 2. Okay, so at the x point, I've got this. My delta, we just said, is Eg over 2, so I'm just going to use that. I got Eg over 2 quantity squared. That's my delta squared. When k equals pi over a, I had that sine ka over 2, and k is pi over a, so I get sine pi over 2. Right? When k equals pi over a, that sine term, that ka over 2 just becomes pi over 2. And sine pi over 2 is 1. Right? So my off-diagonal term just becomes 4t squared. Right? Because I had 4t squared sine squared ka over 2, but when k is pi over a, k over a over 2 is just pi over 2. And sine pi over 2 is 1. I'm going to choose a reference energies. I'm going to call my valence band edge, which is equal to this epsilon A. I'm going to say that that is my 0 in energy. And so then my conduction band edge, EC, is just EG over 2 plus root EG over 2 squared. Right, this is my height. I get always two eigenvalues, that EG over 2 plus or minus square root. So the higher energy is my conduction band, and that's what that's going to be at k equals pi over a. There's nothing, to go and calculate the eigenstate, there's nothing pretty that comes out from it. It doesn't break up. I'll just write down what you would need to do. We don't really need to go through with it. So if I wanted to calculate my eigenstates of the conduction band edge, I subtract off E from my Hamiltonian, which at pi over A is just this EG over 2 quantity squared. So I had an epsilon C in the corner, which is now equal to EG, right? Epsilon C is now my band gap because my valence band is at 0. Right? Epsilon C is my band gap because I set my valence band equal to 0. And so I have my band gap minus EG over 2, which gives me that EG over 2, and then minus that square root term. And then I have my I 2t minus I 2t and minus EG over 2 minus the same square root term acting on C1, C2 equals 0. And you go ahead and solve that. It doesn't give you, it just gives you values for C1 and C2, which I'm not too concerned about. I just want to show you the nature of the wave function. So I'm going to get whatever these C1 and C2 values are, and then psi is equal to C1 S, comma, K equal to pi over A plus C2 PZ K equal to pi over A. That's going to be my wave function, whatever C1 and C2 come out to be. And so at X, my orbitals, this is probably all we really needed to look at, K equal to pi over A. The nature of these orbitals is 1 over root n, these Bloch sums, sum n Sn e to the I pi over 2 plus n pi. And this thing is just equal to I times -1 to the n. That's just I times -1 to the n. Because e to the pi over 2 is I. And e to the in pi is just -1 to the n. And similarly for the pz orbital, which is just negative, again, this is just -1 to the n. So this is my basis that I'm using, and so this wave function is just a linear combination of these two Bloch sums at the x point. And, you know, the thing is, these are, the sign of these is alternating every unit cell, right? An alternating sign every unit cell at the x point. So, you know, this wave function at the x point is rapidly oscillating, right? The unit cells are like 1.5 angstroms apart, and the sign of the wave function at the x point is alternating every unit cell, right, from plus and minus 1. So it's a rapidly oscillating wave function. And that's the nature of any wave function at the x point. It's very different from, you know, the wave function at the gamma point at k equals 0. At k equals 0, the wave function is just uniform. Every unit cell is the same. At the x point, it's flipping sign, plus minus 1, every unit cell. So it's a rapidly, if you're drawing, it's just a rapidly, you know, oscillating function. Every unit cell, it changes its sign.